We will now start learning about Module 1, wherein we will talk about application architecture patterns in Azure. This module introduces and reviews common Azure patterns and architectures as prescribed by Microsoft Patterns and Practices team. Each pattern is grouped into performance, resiliency, and scalability categories and described in the context of similar patterns within the category. After completing this lesson, we will be able to locate and reference the cloud design pattern documentation. We will be able to locate, reference the Azure Architecture Center. We will be able to describe various patterns pulled from cloud design patterns. We will start with lesson 1 and we will also cover lesson 2 in this particular video, wherein there are two different topics. You have design pattern resources is one of the topic, and the second topic is performance patterns. So we'll start with lesson 1, which is design pattern resources. So this lesson introduces the resources available on Microsoft's website that deal with architecture and design of solutions hosted on the Azure platform. After completing this lesson, we will be able to identify and use the pattern and practices cloud design patterns, and we will be able to locate the Azure Architecture Center. So let's start with the question, why patterns? So many common problem areas in computer science have been explored and experienced by a variety of professionals. As with any discipline, best practices have been conceptualized, proven, and prescribed as the most effective or efficient way to solve common problems. Many professionals rely on these best practices so that they can work more efficiently and focus on obstacles unique to their actual problem space. In software engineering, these best practices are commonly referred to as design patterns. So in software engineering, a design pattern is a general reusable solution to a commonly occurring problem within a given context. In software design, a design pattern is not a finished design that can be transformed directly into source or machine code. It is instead a description or template for how to solve a problem that can be used in many different situations. So there are many different patterns that already exist in the industry. So in this course, we will focus on patterns that are domain specific to the cloud. While examples of these patterns may be implemented in Azure or using .NET Framework, most cloud patterns are language agnostic in their design and can be implemented universally across wide variety of cloud providers, programming frameworks, or operating systems. Next, let's move on to Microsoft Patterns and Practices. So Microsoft Patterns and Practices is a long-standing group at Microsoft that collects, authors, and shares best practice documentation for the benefit of the community. The team's intention is to provide anyone a stable technical foundation to start from when building elegant solutions built in any language and hosted on any platform. Most solutions from Patterns and Practices incorporate many different Azure products and technologies as part of the overall solution. The team has been responsible for well-known solution libraries like Prism, Unity, and Enterprise Library. When we talk about cloud design pattern, the team at Microsoft has collected 24 design patterns that are relevant when designing the architecture of a cloud application. Each pattern includes a brief discussion of the benefits, considerations, and implementation of each pattern. The collection of pattern is not meant to be comprehensive and is instead focused on the most popular design pattern for cloud applications. The guide consists of a collection of web pages, each individually focused on a pattern. The pages are broken down into sections describing the problem domain, a high-level technical solution, how these patterns solve a problem, considerations when using the pattern, an example implementing the pattern, and when the pattern is suitable. The patterns included in this guide can be used in many ways, like implementing the sample code as a starting point for your own cloud application, or using the context, problem, and solution sections of the pattern's web page as discussion points during the architectural design session. Or you can use the example section of a pattern's web page to teach colleagues about design pattern, or even you can use the issues and considerations section of a pattern's web page to identify common issues in your problem space. The reminder of this module is that it will focus on a subset of patterns from the cloud design pattern documentation and explain why they are important to understand and how they will relate to the decisions we will make as an Azure architect. So Azure has a very interesting center called is the Azure Architecture Center. So while you can also see that cloud design patterns is a collection of developer-oriented prescriptive architecture guidance, there are examples which are provided in the context of Azure and C#. It includes topics and patterns that help you design your own cloud solutions, and you can easily tweak it to your own requirements. These are some of the links which you can refer to. So for example, the first link is the GitHub link, wherein you can get Microsoft practices and patterns repository on this particular website. The next link is basically for a specific implementation, which is a microservice implementation in Azure. So again, for this you have some best practices when designing a microservice solution running on Azure using Kubernetes, which is also available on the GitHub portal. We'll go through these links, and we will also understand the Azure Architecture Center, and we'll see how the link looks like. So the Azure Architecture Center is a landing page that contains links to documentation written by Microsoft Patterns and Practices team, the Azure product group, and the Azure subject matter experts on architecting solutions for the Azure platform. The center contains links to resources such as reference Azure architectures, cloud design patterns. You have best practices for cloud applications. You have Azure building blocks. You have running SharePoint server on Azure guidance. You have performance anti-patterns. You have Azure and SQL Server customer advisory. You have identity and management for multi-tenant applications. You have Azure for AWS professionals, and you have microservice guidance for Azure using Kubernetes and Azure Container Service available in this particular location. So Azure Architecture Center features all of these things on this particular link. We'll go through it towards the end of this particular video. Moving on, we go to lesson 2, wherein we learn about performance patterns. This lesson introduces patterns related to the performance of the application and workloads on Azure. So after completing this lesson, we will be able to describe the Valet Key pattern, describe the command query responsibility segregation pattern, and describe the throttling pattern. First, we'll go ahead and discuss about stateless applications. So a modular application is divided into functional units, also referred to as modules, which can be integrated into a larger application. Each module handles a portion of the application's overall functionality and represents a set of related concerns. Modular applications make it easier to design both current and future iterations of your application. Existing modules can be extended, revised or replaced to iterate changes to your full application. Modules can also be tested, distributed, and otherwise verified in isolation. Modular design benefits are well understood by many developers and architects in the software industry. So you can see that this is an example of a photo sharing application which is running on a single virtual machine. So all these different modules, which is web frontend, signal R hub, image processor, and thumbnail storage, are different modules which are part of the same workload which is running on the same virtual machine, and it is in different partition. So as you can see, the web frontend shows thumbnails of image users that they have uploaded. Application code takes an image that a user uploads, processes it into a thumbnail, and then stores the thumbnail. The Signal R hub notifies the client web browser the image is finished processing. So you have your virtual machine which is running your Signal R hub. You have storage service which stores your thumbnail. You have web apps, which is your front-end application that the user is accessing, and you have background worker, which is processing your image, which is getting stored in the storage account. So each component of the application can be scaled in isolation to meet its specific demand. So it is totally moving from the monolithic structure to a more modular and scalable architecture. All right. Now we move on to the Valet Key pattern. So cloud applications might allow some resources to be downloaded by the end user. This can result in a tight dependency on storage mechanism, and apart from being an overhead to the cloud application itself, so you need to consider a scenario where a hosted web service offers an expansive set of functionality, which includes downloading and streaming images to the user. In such a scenario, the application could spend a considerable amount of its processing power and memory just to download the images. Because of specific load patterns, the application may limit resources to other tasks to ensure that it handles all of the download requests. This is not an ideal situation and can occur if you have scenario where your application needs to validate the user before downloading the protected images. So the Valet Key pattern introduces a mechanism where your application can validate the user's request without having to manage the actual download of the media. Both can occur while keeping the media private and locked away from anonymous access. The pattern specifies that the client needs to send a request to the web service or application if it wants to access a media asset. The application then validates the request. If the request is valid, the application goes to the external storage mechanism, generates a temporary access token, and then provide the URI of the media asset to the client. Along with temporary access token, the application has now processed this request and can now move on to the other request. It is up to the client application or browser to use the URI and temporary access token to download the media asset. Now the storage service is responsible for scaling up to manage all the requests for media while the application can focus solely on other functionalities. Now, apart from the Valet Key pattern, we will also understand the CQRS pattern, which is your command and query responsibility segregation pattern. So segregate operations that read data from operations that update data by using separate interfaces. This can maximize the performance, scalability, and security, supports the evolution of the system over time through higher flexibility, and prevents update commands from causing merge conflicts at the domain level. So in traditional architectures, the same data model is used to query and update a database. That's simple and works well for basic CRUD operations. In more complex applications, however, this approach can become unwieldy. For example, on the read side, the application may perform many different queries, returning data transfer objects with different shapes. Object mapping can become complicated. On the right side, the model may implement complex validation and business logic. As a result, you can end up with an overly complex model that does too much. So read-write workloads are often asymmetrical with very different performance and scale requirements. So there are often mismatch between the read and write representation of data, such as additional columns or properties that must be updated correctly even though they aren't required as part of the operation. Data contention can occur when operations are performed in parallel or the same set of data. The traditional approach can have negative effect on performance due to load on the data store in data access layer and the complexity of queries required to retrieve information. Managing security and permission can become complex because each entity is subject to both read and write operations, which might expose data in the wrong context. What is the solution to this problem? So CQRS addresses separate reads and writes into separate modules using commands to update data and queries to read data. Commands should be task-based rather than data-centric. So like for example, book hotel room, not set reservation status to reserved. Commands may be placed on a queue for asynchronous processing rather than being processed synchronously. Queries never modify the database. A query returns a DTO that does not encapsulate any domain knowledge. So the models can then be isolated and then they can be easily used for your own application. So having separate query and update models simplifies the design and implementation. However, one disadvantage is that CQRS code can't automatically be generated from a database schema using scaffolding mechanism such as ORM tools. For greater isolation, you can physically separate the read data from the write data. In that case, the read database can use its own data schema that is optimized for queries. For example, it can store a materialized view of data in order to avoid complex joins or complex ORM mappings. It might even use a different type of data store. For example, the write database might be relational, while the read database is a document database. If separate read-write databases are used, they must be kept in sync. Typically, this is accomplished by having the right model publish an event whenever it updates the database. Updating the database and publishing the event must occur in a single transaction. So what are the benefits of CQRS? It provides independent scaling, which means that CQRS allows the read and write workloads to scale independently and may result in fewer lock contentions. Then it provides optimized data schemas. So the read side can use the schema that is optimized for queries, while the write side can use the schema that is optimized for updates. It provides security, so it's easier to ensure that only the right domain entities are performing writes on the data. It provides separation of concerns, so segregating the read and write sides can result in models that are more maintainable and flexible. Most of the complex business logic goes into the write model. The read model can be relatively simple. And then finally, it provides simpler queries. So by storing a materialized view in the read database, the application can avoid complex joins when querying. So when to use this pattern? So one of the scenario is that you can use CQRS pattern in collaborative domains where many users access the same data in parallel. So CQRS will allow you to define commands with enough granularity to minimize merge conflicts at the domain level and conflicts that do arise can be managed by the command. Moving on from the CQRS pattern, we go to the throttling pattern. So, throttling pattern control the consumption of resources used by an instance of an application, an individual tenant, or an entire service. This can allow the system to continue to function and meet service level agreements even when an increase in demand places an extreme load on resources. So what is the context and problem? So the load on the cloud application typically varies over time based on the number of active users or the type of activities they are performing. For example, more users are likely to be active during business hours, or the system might be required to perform computationally expensive analytics at the end of each month. There might also be sudden and unanticipated bursts in activities. If the processing requirements of the system exceed the capacity of the resource that are available, it will suffer from poor performance and can fail. If the system has to meet an agreed level of service, such failure could be unacceptable. So there are many strategies available for handling varying load in the cloud, depending on the business goals for the application. One strategy is to use auto-scaling to match the provisioned resources to the user needs at any given time. This has the potential to consistently meet user demand while optimizing running cost. However, while auto-scaling can trigger the provisioning of additional resources, this provisioning isn't immediate. If demand grows quickly, there can be a window of time where there is a resource deficit. So what is the solution? So an alternative strategy to auto-scaling is to allow application to use resources only up to a limit and then throttle them when this limit is reached. The system should monitor how it's using resources so that when usage exceeds the threshold, it can throttle requests from one or more user. This will enable the system to continue functioning and meet any service level agreements that are in place. The system could implement several throttling strategies, including rejecting requests from an individual user who's already accessed system's APIs more than n times per second or a given period of time. This requires the system to meter the use of resource for each tenant or user running an application. Then there is another strategy which includes disabling or degrading the functionality of selected non-essential services so that essential service can run unimpeded with sufficient resources. For example, if the application is streaming video output, it could switch to a lower resolution. Another strategy is using load leveling to smooth the volume of activity. This approach, basically in a multi-tenant environment, this approach will reduce the performance for every tenant. If the system must support a mix of tenants with different SLAs, the work for high-value tenants might be performed immediately. Requests for other tenants can be held back and handled with backlog when the backlog has eased. Another strategy is deferring operations being performed on behalf of lower priority applications or tenants. These operations can be suspended or limited with an exception generated to inform the tenant that the system is busy and that the operation should be retired to a later stage. A question that one should answer is which Azure service implements SaaS token feature that you can use in the Valet Key pattern we just discussed. Storage account can efficiently use this particular capability. Right now, we will move and visit some of the links that we just discussed and see the Azure Architecture Center. We'll see the Valet Key pattern page. We'll go to the GitHub side and see all of it. So this is the Azure Architecture Center. You can use this link to browse to this particular page, wherein you get a lot of different capabilities, options, documentation to work on the architecture side of the Azure. So in this particular center, you have Azure Application Architecture Guide, which provides you with and helps you to design scalable, resilient, and highly available applications. You have reference architectures. You have Microsoft Cloud Application Framework for Azure. Furthermore, you have various different capabilities where you can, for example, if you want to build microservices in Azure, you have the design guide, you have Azure Data Architecture Guide, you have the high performance HPC computing guide on Azure, Azure building blocks, Azure for AWS professionals, etc. This is a very excellent a site, and this is the page from where you can actually learn a lot of different things when you are working on learning how you can architect solutions in the Azure platform. Furthermore, if you want to go ahead and learn more about Valet Key pattern, this is the link that you can access. Apart from that, there are multiple patterns which are available. If you just scroll down this particular table of content, you can see all these are the different cloud design patterns, from ambassador to anti-corruption layer to command, query, and responsibility segregation pattern that we just discussed. Then on the GitHub portal, you have the repository for Microsoft patterns and practices. So you have 22 patterns and reference architectures which are available. Then for specific application, for example, if you want to implement microservices on Azure, you have specific applications available that you can implement via the Microsoft Azure Kubernetes services as well. And finally, this is the link from where you can access the Azure Architecture Guide, and you get every other capability under this particular section. And it gives you how you can use this guide in a more suitable fashion for your own problem statement. So with this, we come to an end to this particular video. Next, we'll discuss in lesson 3 resiliency patterns.